IIT Patiala, Engineer I.S. Oberoi, FIE, Honorable Secretary, IEI Faridabad Local Center, all the delegates from different parts of the country participating on virtual mode, all the delegates from academia, R&D organizations and industries, and all the executive members of IEI Faridabad Local Center, and my dear student research scholars. It is my proud privilege to be here today with all of you with this technical national webinar on advanced material synthesis, characterizations and applications. I am really thankful to the organizers for giving me an opportunity to address this august gathering. Materials have become very important in our day-to-day lives. Materials are more significant in our culture than we realize. Transportation, housing, clothing, communication, reactions, and food productions, and virtually every segment of our daily life is influenced by materials. So materials have contributed to the advancement of a number of technologies, including medicine and health, information and communications, national security and space, transportation, structural materials, arts and literatures, textiles, personal hygiene, agriculture and food science, and the environment. In all the field, every material is spreaded, and these interdisciplinary interactions between the material science and other fields in the development of new materials and their applications is to be understood well. So the national webinar on advanced materials, their synthesis, their characterization, their applications are being organized by Institute of Engineers India Faridabad Local Center today, that is on 29th April 2023, is a burning topic of the day. And this webinar will focus on cutting-edge synthesis techniques developed in the field of materials, manufacturing technologies, and advanced state-of-art characterization tools and methods to evaluate the ultimate properties for their functional applications. No doubt, this webinar will be providing a wide national forum or platform for researchers, for industry practitioners, for hardcore manufacturing engineers working in shop floors to share their new ideas, original research results, and technical developments. We are thankful to all the invited speakers, as it has been mentioned by the chairman of Faridabad local centers, all very, very renowned invited speakers for leading academy, industries, and institutions and industries who are going to deliver a comprehensive overview of the present status and potential future directions for research in processing of advanced materials. Industries certainly will look forward to utilize the research outputs in collaborations with academics and the R&D organizations. Metallurgical and Mineral Engineering Division Board of IEI headquartered Calcutta is doing extremely well to spread the knowledge in metallurgical and materials engineering through organizing various webinars, seminar, workshop, national convention, etc. throughout the country. Therefore, this is one of the webinar is being organized today by our Faridabad local center. Once again, I thank the organizers for this webinar, for inviting me and giving an opportunity to address the galaxy of intellectuals from R&D organization, from academic institutions and industry. I wish all the success of this webinar seminar. Thank you. Thank you very much.
Thank you. Thank you. Thank you. Thank you. Thank you, Dr. Bhoi, for your enlightening message. And it was really wonderful to have your thoughts on this subject of today's webinar. Yes, today's webinar is a burning topic. We have to work, think about new materials and their synthesis. And that's very important that this webinar has been curated by Faridabad Local Center. And we earnestly thank you for sparing your time and giving us a direction to this webinar. Moving ahead, Engineer Devnath has not joined us, so we'll go ahead with the next session. I would now like to invite our eminent Faridabad Local Center member, Dr. Shivraj Singh Kasana ji. He is BE Metallurgy, has an illustrious industrial career of more than 4 decades, and he's presently working with the company Star Wire India Limited, and he's Executive Vice President Quality and R&D. He has a passion for innovation and new research, which has prompted him to do PhD Material Sciences 2021 from School of Physics and Material Science, Thapar Institute of Technology, Patiala. He has also played a key role in developing import substitutes by developing or Indianizing the materials, processing technologies through innovation and continuous supports. So we would now invite Dr. Kasana ji to take over the proceedings and kindly introduce the speakers and go ahead with the webinar. Dr. Kasana.
Okay. Okay, thank you very much, Mr. Oberoi. And I thank you, Dr. Bhagdar Bhoi sir, and our chairman, Dr. Engineer Kuldeep Raj Gupta ji, for giving me this opportunity to work on this webinar and try to put some things into some words which are relevant for today's modern era. So basically, materials are very, very important ingredients for any society. And the society's progress or advancement is judged by the amount of advanced materials they are making. Any country which is advanced or not advanced, developing country or developed country, it depends upon the kind of materials it has already developed, and it is doing the development of advanced materials. Because today we have walked from, say, Stone Age to modern era, where we are talking about intelligent materials, artificial intelligence, and use of all these, latest techniques. Even industry is not far behind. They are working on Industry 4.0 and going ahead with, shoulder to shoulder along with the researchers. So it is very good opportunity. Why this webinar is important and relevant for today's time is that unless we know the materials, it is very difficult to know their applications, to know exactly how we have to use those materials, and to know about their characteristics under various service conditions. So you take an example of some failures, say failures of Titanic. It happened because of we were not knowing about the material used in the bottom plate of the Titanic. And it failed because of impact transition temperature. The impact transition temperature was much, much higher than room temperature. So when it strike with the tip of iceberg and further, say, amount of ice, that bottom plate got cracked. Suddenly it changed from ductile to brittle material and it failed. Similarly, the failure of NASA's Space Shuttle Columbia, it failed off because of while it was coming back from space, it was coming back to Earth. A lot of heating took place in one of the tiles. Insulating tile got heated up and it gave way and melted. And so many astronauts, coming into that shuttle, they got burnt into it. It was a very tragic incident. Even one of our astronaut, Kalpana Chawla, lost her life into this. So this is why the materials are very important. It is very important to know about the material. It is very important to characterize the materials. So in this webinar, as Bhagdar Bohisar has already mentioned about what this talks about, I will be talking about, say, what our eminent speakers have covered into this. They have covered three areas. Dr. Ravi Kumar has covered a very nice topic of use of industrial waste and then converting into very strong, mechanically strong, say, dielectric metal matrix composites by converting the slurry, grinding slurry into powders, maybe sometime nano powders also, and then using them as composites, which are very, very important. Other than that, his project can be used in utilizing the, say, industrial waste. Grinding dust is generated wherever grinders are used. So centerless grinder or cylindrical grinder, wherever grinding is done, the material is removed, that material is getting into waste. It makes a slurry. And similarly, in steel plant, in our Star Wire India Limited, we generate at least 500 to 600 tons of, this dust every month, and that we are recycling into AOD or some remelting. But it is not so safer. In case the same can be converted into some pellets and all, then the recovery could be much better. So he has covered this topic very nicely, and he will be giving. I'll introduce him when his turn comes. But he has very illustrious career of working on smart materials. More than 20 years he has been working on smart materials. Then another speaker, Mr. Raj Bahadur, he will be talking about synthesis and characterization of synthesis and characterization techniques. And in synthesis, he will be talking about ECAP, this equal channel angle processing, then ARB, accumulated roll bonding, and HPT, deformation, high pressure torsion deformation techniques, where he will be working at high strain rate formation, which result into very high level of properties into the same material in comparison to the conventional methods at conventional strain rates. The very good example is, say, deformation of low alloy, you can say 300 series. All 300 series, in case not deformed at proper strain rates, they result into coarse grain materials. So that is the disadvantage which can be overcome by going for high strain rate forming of these materials. So he will be covering this topic very illustriously. And then third speaker, Dr. Hitesh Kumar, he will be elaborating upon, say, effect of grain orientation and crystallographic orientation by thermomechanical processing on dual phase perlitic steel. So that will be enhancing the oxidation and corrosion resistance of this material. So these are the basic topics which will be covered into this webinar. And one by one, when the authors, speakers will come, I'll introduce them about their profile also. So that's all. I think we should start for the first speaker, if you permit me.
Sir, please go ahead. Please go ahead, sir.
Okay. Dr. Raj Bahadur, are you ready?
Yeah, I'm ready, sir.
So Dr. Raj Bahadur is a PhD from IIT BH, and after post PhD, he has around 7 to 8 years experience as assistant professor in various institutions like GLA University Mathura and GL Bajaj Institutes in Mathura, and stay in NIT Hamirpur. He has been working since 2019 as assistant professor in Department of Material Science and Engineering as assistant professor, and he is having a very keen interest in working on this high energy rate forming processes. So I request him to start his presentation on this synthesis and characterization. Dr. Raj Bahadur.
Yes.
I'll just like to interject in it. I'll request all the attendees If you have
Yeah.
any questions, kindly put on your question answers in the panel, and we'll have a separate question answer session, and all the worldly speakers would try to answer your queries. So that question answer sessions will be open. Kindly put your question answer sessions. Thank you.
Because time is very stipulated 20 minutes, so that is why we will have to maintain our time limits.
Yes,
So
sir.
question answer session has been kept separately.
Please go ahead, sir.
Go ahead, please.
Yeah, so my slides are visible.
Yeah.
Yeah, so first of all, I would like to thanks to the organizers to invite me here, and good morning to all. So my topic is advanced material processing techniques, mechanism, microstructure, and mechanical properties. So I will quickly go through the presentation because time is limited. As Sir has said already, that if somebody has some query and some doubt, you can ask in between also, and then some after that. So first of all, I would like to uh, discuss the few strengthening techniques in the materials. Okay, so the strength hardening, grain boundary strengthening, solid strengthening, hardening, dispersion strengthening. So just I was planning to discuss one by one in detail, but the time is limited. So nutshell, in all these techniques we have the mechanism, the basic mechanism, how to produce hinders in the dislocation motion during the plastic movement. If we can produce more and more hindrance in the path of dislocation motion, then we can do the strengthening of that material. So all these techniques basically based on this fundamental. Okay, so if you can produce by increasing the grain boundary length or introducing the more and more dislocation or solid solution strengthening, that is allowing only precipitation hardening is also if you heat the material at certain temperature, second phase particle are there, so they act as a again hindrance in the dislocation motion and dispersion strengthening. So why this plastic deformation and other things are important, and here we have this particular technique, the strengthening technique is the grain boundary strengthening. So I would discuss this technique in the further presentation. So grain boundary strengthening is nothing but the increasing the length of the grain boundary in the material, or you can say the reducing the grain size of that material. So both way or both are the same thing, and we can create the more and more hindrance in the path of dislocation. Okay, so if the grain size is coarser, then dislocation move easily. If the grain size is let's say uh, fine, then the dislocation, the path for movement of dislocation is less. So that means the grain boundary, sorry, the dislocation is moving, then it will find some obstruction. So that has to act as a hindrance, and therefore we can say the strengthening will take place because we have to apply more and more load to deform the material. So here the literature is very crisp information is here. If we have the grain size in the range of 0.2 to 0.5 micron, okay, so this is the ultra fine grain, you can say the strength is very high. Okay, it's around 1000 megapascal yield strength when the grain size in the range of 0.2 to 0.5 microns. And if you see the ductility of the material or elongation of that material, then at that level the ductility is very less, it's 0.2 to 0.3 micron. The ductility is less than the 10%. And if you see carefully this region of 1 micron to 10 micron, then the ductility is very high. So here idea is to combine the two things, the section of the microstructure of the ultrafine grain with having some coarser grain of the range of 1 micron to 10 micron, then we will have the optimum properties in the material with high strength and high ductility, we can say. So coming to the plastic deformation, so you can see this is schematic of the plastic deformation by rolling, in that we are deforming the material plastically. So the number of things are happening in the material. So these are the schematic of the different features in the microstructure when we are deforming the materials. Okay, so this is the shear band. First of all, at microscope level or microscopic level, you can say these are the shear band formations. And within a grain, if you see, then deformation bands are there. So these are the within a grain, different orientation you will see. Then these are called as deformation band. And then if you try to focus in particular deformation band, you will find this kind of distribution structure, and we can call them as a substructure also in the material. And finally, if you see, look at that closely after deformation or after severe deformation, then distribution structure is there. So what we have, I have said in the initial slide, the strengthening is depending on how much hindrance we can produce in the path of dislocation during the plastic or during the plastic deformation. So if we are trying to deform and we have more and more obstruction in the path of dislocation, then it is difficult to deform the material, and therefore strengthening of the materials takes place. So this is the basic mechanism behind the strengthening in this technique, in this basically with the microstructure features. So these are the things I have shown. So let us come to the results of the plastic deformation. So this is the microstructure of low carbon steel, which is having the carbon 0.08%, very less carbon it has, and it has very lesser strength also. So in that in that microstructure, it's basically EBSD micrograph. So electron backscatter diffraction, we have by this technique we have taken the image. So this is undeformed material. First one is, and second one is equal. It is deformed through equal channel electroplacing. So you can see now
there's some problem in voice.
Dr. Raj Bahadur, if you can disconnect your earphone, is it possible?
I am doing with the desktop.
You.
So now it is audible.
Yeah, it is audible.
Okay. So let me do this here. Yeah. Okay. So this is the micrograph of the low carbon steels. After deformation, before deformation, you can see the coarser grains, and after deformation, you can see the sub grains are start forming, or deformation bands are start forming within the grain. You can see, and if we are keep on increasing the level of strain or keep on deforming the material, same material, then you can see the refinement of microstructure. Okay, so you can see here the very fine grains, and this is the accommodation of almost 9 equivalent strain on the material. Then you can see the microstructure is fine, is like anything, so it is in the range of ultra fine grain, or you can say the typical grain size is 0.2 micron. So this is the result of severe plastic deformation, basically of E-cap deformation. Okay. And if you see the electron micrograph, basically transmission electron micrograph, in that you can see the features which are very fine. The grain size, you can say it's 0.2 micron, level 0.2, 0.3 micron. And this is this dislocation structure we have captured. It's very higher magnification. So these are the dislocations dislocations are accommodated in the materials, and later they act as a barrier in the path of the dislocation itself. Okay, so that's how the strengthening takes place in the material. Now coming to the SPD techniques, so these are the various SPD techniques I'm going to discuss one by one. So first is high pressure torsion. So in that we have the very small sample having the diameter 0.1 to 2 micron only, and diameter 10 to 20 millimeter. So by these techniques, before I discuss all these techniques I will discuss. The beauty of all these techniques is the cross section of the material is not going to be changed even after very severe deformation. Okay, like rolling, if you deform 50%, then here this cross-section area will be reduced, and after some extent of rolling, you will not able to deform the material further. So you can only impose strain in the conventional process up to limited of some limited strain only. But here you can accommodate, or you can impose strain like 100 uh, equivalent strain 100. So it's like 10,000 percent by these techniques. Okay, because if you deform the material, the cross section area is not going to be changed. It will remain same. Okay, because it is in a cavity, and there's a plunger. We are rotating the plunger by applying some very high load. So in that way, we are deforming by material by doing shear on that material surface, and we can calculate the strain imposed by this formula. Okay, 2 pi nr. So n is the number of rotations, r is the diameter of the sample from the center, and h is the thickness of the sample. Okay, so coming to the ARB, so in this techniques, it's a very simple techniques. You all understand the rolling process. So in that we have the two pieces of the sheet, and we stack together by cleaning the surface, and at certain temperature we roll that material by reducing the area 50%, and again we will have a similar thickness what we have started. Okay, so if you are keep on repeating the uh, deformation by this technique, since again you cut it and stack together again and again you deform it. So number of cycles we can repeat on this. So and after some number of cycles, you will find the material is refined like anything. So it is in some ultrafine grain you will achieve for sure. But it's also depends on the materials, the formability of the materials, or whatever ductility is there. If the material is not sufficiently ductile, then you cannot deform the material by this technique. And coming to the multi-directional forging, then this is again we can have the cross-sectional area intact after end of the process. So step one, you can rotate the sample in particular directions and keep on deforming by the forging process. And at the end of the process, you will find a similar kind of cross-section. And at the same time, we have imposed a lot of strain in the material. So microstructural features like will be defined, and dislocation test will be increased like anything. So the mechanical property will be enhanced many times of the coarse grain as compared to the coarse grain material. I will discuss the mechanical properties also in the last. So next technique is twist extrusion. So it's a very simple process. We have this kind of material, and we have a die which is having this kind of shape in the channel. And if you pass this material through this channel, then you will get you are deforming the material plastically, but the next channel is following channel of twisting channel is again the similar means you can say like the square channel, and after deformation the shape is changing, but during deformation shape is changing, but as you are completing the process and we are passing this twisted material through a normal channel, even then you will find this kind of material. But we have deformed the material again plastically or sever plastically, and then the features will be defined and mechanical property will be improved. So this is the again the new technique. This is repeated corrugative pressing and straightening. So in that process, we have a sheet or material. We have pressed it, and after pressing, we will have this kind of shape of that sheet. And again, you deform that material by flat dies, and you will have the similar kind of material. Okay, and essentially this whole process in a closed cavity. Okay, otherwise it will expand. Chance of expansion of the sheet, and then in that case we cannot uh, we maintain the cross section of the material. So this is the formula by which we can calculate the equivalent strain. during this process. So coming to the equal channel angle pressing, so this is the simple process as compared to the other techniques and relatively higher dimensional sample we can deform. Okay, so this is the channel. So we have the basically two angles, is outer arc angle and inner intersection angle. So the strain imposed is depending on these angles. So this angle sometimes 90 degree, sometimes 120 degree, 120 degree, depending on the material. If material is more ductile, we can deform the material by 90-degree die. If the material like steels are not that ductile, then we can deform it by increasing the angle so that it can easily be deformed. Okay, so the strain imposed in that case is depending on these materials on these angles only, this phi and psi. So basically, this is also having the deformation mechanism is shear. So different routes we can use. Now coming to the results of this E-capped material. So this is again optical micrograph of adhesive low carbon steel. We have deformed that material, and you can see the dimension of the different thickness of these grains, very small, and we keep on uh, deforming the material by these techniques. Then you will find uh, the grains are more and more fine after each pass. So this is the uh, final micrograph after 28 pass of the steel, the low carbon steel. Then you will find the almost aqueous grains are forming of the dimension basically 0.2 to 0.3 micron. So and we have also calculated the dislocation density. So dislocation density is also very high. So we have refined the grain size. We have introduced more and more dislocations. So this is the good recipe to increase the strengthening of the strength of the material. Okay, so because uh, we have introduced a lot of boundaries, so a lot of boundaries are there, increased number of boundaries and dislocation density. So both are hindrance in the movement of the dislocation, and if the movement of dislocation is difficult, then obviously we have to apply more and more load to deform the material, and we can say our material get strengthened. That's why we need to apply more and more load to deform the material. So this is the mechanism. I will not discuss. I will directly coming to the mechanical properties. So this is the low carbon steel, where having the very low strength around 230 or megapascal yield strength, and we have deformed the material up to 28 passes, and you can see its yield strength increases up to around 900 or more than 900 megapascal. Okay, so the reason of increasing of the strength of this material after ECAP is basically refinement of the grain size and increase of dislocation density, and also the texture developed during this process. Okay, so that I have intentionally not put in the slides the texture part, but we have analyzed and we have calculated the contribution of the texture and the strength also. Now coming to the one another material, which is inconel 800, incolloid 800, which is we have received from Dr. Kasana only, and you can see this black graph which is showing the. So I'll show the data here. So we have done this room temperature and high temperature test of that material after ECAP and before ECAP. So you can see before ECAP, the yield strength of this material is around 217 megapascal. At high temperature, at 600 degrees Celsius, the strength is only 152 megapascal. This I'm talking about the yield strength. Okay, and and we have done the ECAP of that material, and we have tested at room temperature. So you can see the strength or the yield strength of this material is increases around 800 megapascal after only one pass, and we have tested at room temperature, and we have tested this material at 600 degrees Celsius, and you can see the yield strength of that material is increases to still means it is not decreased like anything. It is still 502 megapascal at 600 degrees Celsius. So it is far more than the edge material or undeformed material, which is 152. So we can say it is almost more than 3 times of the edge material at high temperature as well as a low temperature. So at high temperature, the strength is intact. Okay. So this is the graph. The similar things it's showing. We have this edge material of Incolloy, and this is the room temperature, and this is the high temperature of adjacent material, and this is the graph of deformed material at room temperature, and this is the graph of deformed material at high temperature. So you can see, you can compare the adjacent material at room temperature, this, and deformed material at room temperature, deformed material, undeformed material at high temperature, and deformed material at high temperature. So it is strength is improved. The reason again, the refinement of the grain size on increasing the grain boundary length and increasing the distribution density also. So coming to the conclusion, so advanced plastic deformation techniques are able to impose high equivalent strain on metal and alloys without changing the cross section of the workpiece, which is very important. The ultrafine nanograins can be produced by plastic deformation techniques, and preferred crystallographic texture can also be developed in the material by these techniques. So thank you very much for your kind attention. I hope I finished it timely. Thank you very much. So if you have any questions.
Question, Raj Bahadur, Dr. Raj Bahadur will take up after the end of.
Sure, sir, sure. So now I'm stopping.
So yeah, so you can close, and we can now move on to Dr. Hitesh Kumar. Regarding Dr. Hitesh Kumar, he is assistant in Department of Mechanical Engineering in Thapar Institute of Engineering Technology, deemed to be University Patiala. And his work is mainly upon the crystallographic and grain orientation by thermomechanical processing, and producing the say properties by tuning the material to different orientation, crystallographic orientation and grain orientations. So the highlight of his work is that he has been able to give various amount of orientations, and he has found that at certain orientations he is getting much enhanced property in this dual phase perlitic steel, especially oxidation and corrosion resistance, say to the tune of somewhere, I think, up to 30-40% property enhancement he has been able to achieve. So these are the highlights of his say work, and I request him to present his work directly now. Dr. Hitesh Kumar.
Thank you, Dr. Pesana. Thank you for giving me space in this organized symposium. So thank you all. And first of all, I'll give you a brief introduction about me. Myself, Dr. Hitesh. I completed my PhD from IIT Bombay in 2022. And after that, I joined the Thapar Institute of Engineering and Technology as an assistant professor. So my area of research is how the crystallographic texture orientation is going to affect the oxidation and corrosion behavior of perlitic steel. So I'm starting from here. So the brief about the slides. So it will go through the introduction, literature, gaps in knowledge, result and discussion, and then the oxidation behavior of eutectoid steel, and then the corrosion behavior of eutectoid steel, and then the concluding remarks. So the starting point is like when we start off, let's discuss about that. So what is the oxidation mechanism? Like how it is going to be affected? So it's basically affected by the crystal orientation or crystal defects like if something misorientation is there in your material, then there will be providing space for the oxygen to interact with, because it's a highly energy space to the material. Then the surface finish alloying element, definitely environment is also going to affect the oxidation and corrosion behavior of the material. So in earlier literatures, they will talk about mostly the surface finish, alloying, and environment, but the crystallographic texture part still not identified yet. And other than that, it's a solid state transformation when the driving force during the oxidation is basically either the electric field between the charge field between anions and cations, and then the chemical potential difference between both of the layers. So that is going to affect the oxidation mechanism. So when we talk about the oxidation of iron or a steel, it's basically divided into two, according to the temperatures, basically divided into two parts. One is the low temperature oxidation, another is the high temperature oxidation. So if we'll talk about the low temperature oxidation, see there are two phases which are stable, that is hematite and magnetite. The first layer which is going to be formed is basically magnetite, and when the oxidation process carry on, it will going to form the next layer, that is the hematite only. So if we'll talk about from the starting from the substrate, the first layer is a magnetite, the second layer is an hematite. But when we talk about the above 570 degrees Celsius in pure iron, it's basically eutector transformation, where iron substrate and magnetite react and form the boostite. And as oxidation and corrosion is a major problem in most of the steel production units, as well as when we are using it in oil gas refineries, steel products, there is also a big problem. So this problem started, it's basically Tata Steel, like we took this material from the Tata Steel, because they in Worley sealing, they use a eutectoid wires. So there they are getting the corrosion and oxidation problems. So they come to us for a problem to how to enhance the corrosion and oxidation properties of this material. So what we did, we started it with the help of what we did. As you know, it's a dual phase steel, it's a ferritic steel. So one is a ferrite, another is a cementite. It's a lamellar structure of ferrite and the cementite. It's a fully ferritic steel. So in fully ferritic steel, the strength of the materials also depend on the interlamellar spacing. The interlamellar spacing is basically distance between one ferrite and ferrite and cementite between that. So how it is going to, that is basically affect the oxidation mechanical property of material. So this is basically EBSD of different ferritic colonies. So what we did with the help of different thermomechanical processing, we aligned the ferritic colonies in the y-axis direction. And this is done with the help of different thermomechanical processing. So this from where we started our work. So now see how these alignment or a interface crystallography is going to affect the oxidation kinetic of material. So from different thermomechanical processing, the alignment, as you see, 31% aligned mean to say out of 10 colonies, let's suppose there are 10 colonies in a material, out of 10 colonies, 3 colonies are aligned in a y-axis direction. And 66 mean to say out of 10 colonies, 6 colonies now aligned in the y-axis direction. And these thermomechanical processing does not affect the texture much. As you see, most of the texture is a 1001 plane. So material is having the same texture. We only change the alignment of the colonies. So the effect which we are seeing later on is basically due to the alignment. So then these colonies are oxidized at different temperature. One is isothermal temperature situation. When you see, when we heated the material from 300 Kelvin to 973 Kelvin, around 700 degrees Celsius, because at 723 the ferritic colonies is going to be changed into again in the austenite phase. So we only choose till 973 Kelvin. So we can see the alignment of colonies affect the oxidation behavior. So when we are aligning it more, the material getting more oxidation resistance, means the oxidation properties get enhanced. So is it for the this did on isochronal situation? Is it true for the isothermal situation also? Mean to say when we are putting it material at particular temperature for long hours. So as I already discussed in steel, we divided the temperature into two different parts. One is a low temperature where only two phases are stable, and a high temperature where three phases in oxides are stable. So we choose 673 and 873. As you can see, in when we are talking about 66% aligned, the material is getting less oxidized. So material is becoming more resistant to the oxidation. So we calculated the oxidation kinetics with the help of the parabolic law equation, that is y square is equal to mx plus c. So we definitely see as we are increasing the alignment, the material is getting less oxidation. So this basically depends on, now we can comment on it. This is because of the morphology of the paralytic colonies. So is it true for the like why it is happening? Is it true because of the changing of the microstructure of a material, or something is happening with the some different phases are forming on the oxide state structure? So what we did the EBSD analysis of the oxide which is forming. So what we observe, when material is less aligned, 31% aligned, we are getting some cracks in the oxide scale. So why these cracks are forming? So the cracks is basically mean to say the oxide scale which is forming is not much adhesive to the substrate, and these cracks are basically providing a path to oxygen to interact with more substrate and forming more oxide scale. That is the one of the reason why it is happening. But in the case of 66, there are some porosities are there, but not much as comparison to 31%. So this is clearly visible. So we can comment on this. This alignment is basically changing the oxide morphology only, not oxide phases. This is basically morphology of the oxide scale. So is it true for the aqueous corrosion? In aqueous corrosion, we choose different H2SO, we went for the H2SO4 as well as HCl and NaCl3, all or these three things. So we can see when we are increasing the alignment, there is a sudden drop in the sudden drop in the corrosion behavior of a material. The change in alignment of palladic colonies is basically changing the corrosion behavior of the material also. So we calculate the E core, I core, and RP of polarization resistance of the with the in comparison of interlamellar spacing, because by changing the alignment, we are changing the interlamellar spacing also. So this is also affecting the oxidation. Now earlier it affect the oxidation, is parallelly going to affect the corrosion behavior of a material. So the question arises why it is happening, as because of the interlamellar spacing is a nanometer, we can't do the EBSD on the fine of the fine paralytic colonies. So what we thought of, let's grow some coarse paralytic colonies with the help of laboratory scales with the slow cooling. So what we did, we grow some coarse paralytic colonies and mark those in the colonies with the help of micro indents, and did the EBSD on that. And the same reason we corroded in the H2SO4 solution. So what we observe, two things we observe. This is a basically galvanic corrosion, not pitting or not uniform. It's a galvanic corrosion. One is behaving as an anode, another is behaving as a cathode. And we calculate the roughness of the material before before polarization and then after polarization. What we observe when we near to the interface, there is a sudden drop, roughness is increased. So you can see there is the material is basically more etched out near to the interface. So this come out with the theory. interface is basically going to play an important role here. So what we did, we calculate the Ishache and Bagaski relationship with the with these colonies. So Ishache and Bagaski is basically interface relation between ferrite and the cementite. So we, as the material is more near to the Ishache and Bagaski interface crystallography, the material is having more intact, and we can see by deviation from Ishache and Bagaski is increasing. As it is increasing, it is basically increasing the local depth of it. The question is how we calculated the local depth of it with the help of AFM, because we calculated the roughness of the material at the particular colonies, as well as zeta profilometer. So we went on each colony and calculate the with the help of EBSD, calculate the Ishache and Bagaski interface relationship, as well as we calculate the like how much depth, how much material is removed during the corrosion or that. So then we also calculate the stresses. These stresses are calculated with the help of Raman. These are Raman hydrostatic stresses. This in this, what we did, the same way we mark each colony, oxidize it in the controlled environment. Controlled environment means to say 99% there is a nitrogen and 1% oxygen was given, so that the material oxide layer, which is basically forming on the material surface, it should be less, so that we can identify each colonies. So, and then we calculate the Raman stresses on the particular colonies. So what we did, we calculate the Raman stresses through in a line by line intercept method. So first we the oxide which is forming on the ferrite, we calculate the Raman stress on that ferrite phase, then the cementite phase. But we observe near to the interface there is certain enhances there in the hydrostatic stresses which is forming on the oxide scale. These sudden enhance is basically as you know, the stresses in the oxide film may lead to the cracks, because it's basically compressive or tensile stresses. In this phase, it is a tensile stresses which is forming on the material oxide scale. So these stresses is basically providing more pressure on the oxide scale, and it got cracked. So these cracks later on providing the space to the oxygen to interact more with the substrate, and this increasing part is basically becoming the material more oxidation prone. So these all experiments were done on a coarse perlite structure. As the limitation of our new characterization technique, we can't do these experiment on the fine perlite structure. So we can say these indirect measurement, we can say when we are aligning the perlite colonies, the material is becoming the interface is becoming less deviated from Ishache and Bagaski orientation relationship, and those interface is basically enhancing the oxidation resistance and corrosion resistance of material. So in last, I can say the stability of the oxide film and the oxidation kinetics is basically changes with the help of interface crystallography. So corrosion resistance is basically depends on the crystallographic orientation, and the synergy, there is a direct relationship is there between the metal oxide microstructure, which basically affect the oxidation kinetics and corrosion kinetics of material, and change lattice or going to affect the oxidation and the corrosion resistance of material. So these two papers we published in Philosophical Magazine and Scripta Materia recently. So at last, I will thank CUST and Tata Steel for providing us the material. So, and the collaborators, co-workers, and especially IITB and Thapar, because after joining Thapar, I did some of the work here, and they give me the space and give me the space as well as funding to generate that type of enhanced facilities like EBSD, bulk texture, XRD facilities in Thapar. So which so that we can do that part here in the Thapar also. Thank you all. So if you have some questions, you can.
So thank you, Dr. Hitesh. We shall be having the questions in question answer session.
Thank you, sir.
Finishing the third speaker. So I now invite Professor Ravi Kumar, and I'll try to introduce him because as little I know about him, but he is a very non-professional, and initial education he has taken from, say, higher education he has taken from TFIR, Tata Institute of Fundamental Research, as I have been told by Dr. Raj Bahadur. And after that, he had been, say, principal in many engineering colleges and director in Punjab Engineering College, Chandigarh also. And subsequent to that, he has worked in accelerator unit in Delhi for around 10 to 12 years and worked on smart materials. And he had joined NIT Hamirpur as professor. For last 11 years, he had been working on smart materials, and the topic he has selected is very, very useful for industry by utilizing the industrial waste grinding sludge, which is generated in heavy, very large amounts in the industry. And he has taken this noble project. I am really very much impressed by the topic he has taken, and I look forward for much more association with him, because my company itself is generating around 600 to 700 tons of grinding dust, which at present we are using, recycling it in our AOD. After say draining out the water and drying it, we are not able to separate out grinding wheel. So that is the problem. We will be discussing later on with Dr. Ravi Kumar how to separate it out and then make pellets and use for a very, very economic, remelting and recycling of this. So I invite Dr. Ravi Kumar to take over now. Please start.
Professor Ravi Kumar ji, good afternoon. Good afternoon. Dr. Ravi. Thank you. Most welcome, sir.
Okay, thanks for inviting me to talk about some of our new ideas on the powder metallurgy from the waste materials. And today, and thanks for Dr. Shivraj Singh giving a nice introduction. And let me share my presentation. Okay. So, presentation mode. Yes. Okay. Okay. No, I will do. No problem. Don't put fingers. Okay. This panel will be. इसको यहाँ से first वाले पे click करना. Okay. Okay. Yes. So today I will talk about the waste material. Basically, when I gave a talk in general to the
screen sharing.
Please share your screen.
Okay, how I can do?
Not visible.
देखिए जरा visible क्यों नहीं हो रही भाई? Okay, I'll do again. Screen sharing as okay.
You have opened your presentation on your system, sir?
Yes.
And then click on share screen.
Okay. Now it's okay?
Yes, it is okay now, sir.
Okay, okay, okay. And now I'll make it. Now it's okay.
Yeah, it's okay. But it's
Oh, now this talk is
not
different.
coming in slide mode.
Wait. कैसे करेंगे इसको ठहरो. Hold on, please. Sorry for the delay.
Topic is different. Microscopic.
Yeah, that's what I am looking for the.
Your topic should be industrial waste.
Okay. अभी था यार, इसको जरा देखिए यार राजबहादुर. Pause sharing.
सर हो गया ना सर?
हाँ, ये नीचे आ नहीं रहा ना जी. इसको बंद करूं. ये वेट. इसको न्यू शेयर. इस पे करो क्लिक. ये अलग है. करो इसी पे करो आप शेयर करो. नहीं ये नहीं है ये. नहीं आप कर दो बिल्कुल सर एक बार. नहीं ये नहीं है, इसको बंद करना पड़ेगा. वेट, इसको भी बंद करना पड़ेगा. स्टॉप शेयरिंग. एंड नाउ आई विल sir wait presentation share don't worry इसको this is another talk. Sorry for the delay.
No problem, sir. Please take your time.
Actually some now this will be going here. Now I will share. ये वाला शेयर करिए. ये वाला. नो सर, आप this is recycle. वो ठीक बात है, आप ये कर दीजिए, उसको शेयर करिए सर. ये स्क्रीन शेयर कर रहे हैं ना आप. हाँ. इसको चला देना तो स्क्रीन आपकी शेयर हो. इसको शेयर करो ना. ये तो क्या प्रेजेंटेशन खोल दीजिए. प्रेजेंटेशन ये वाला. बस. Okay. Now it's shared.
Yes.
It's visible.
Yes, you can do it slideshow mode, sir.
That I will do, no problem.
It is sharing now.
Okay.
Yeah, it's okay now. Perfect.
Basically, this topic we have selected because we are working from last 4, 5, 6 years on the waste materials like fly ash, like coal fly ash, and as well another waste materials. So here today I will discuss about the recycling of waste metal chips to fabricate mechanically strong and electric metal matrix composite. And this is the work of one of my recently PhD student who got his degree. And there are many problems like pollution problem and their solution, basic of metal cutting, grinding, type and amount of chips production, traditional recycling strategy of chips, sustainable recycling chips, synthesis and characterization of those, and how we can do the mechanical measurement and properties of that. Then we found that these materials are very good electric materials also for the purpose. So there are various kind of pollutions are occurring in a system. So we have to consider what kind of problem we are facing when we are using various kind of cutting and machining machines and the waste material being produced. Can we utilize that kind of waste material? That was the idea behind our talk. The basic mechanism is a turning operation, milling operation, and grinding operation, where the metal is being removed in the form of a chip or in the form of a swath when the grinding mill or the cutting or the milling operations we are doing. So these or when they are being produced, so lot of heat is being generated, and these hot particles or chips, when they expose to the environment, it can give you a lot of waste material. If you visit to many kind of machining and industries, you see it is creating people are just throwing it, and that will enter into the Mother Earth and creating a lot of pollution to the water pollution as well as in the soil pollution in a system. So type and amount of chips we are getting, the total input material in a metric ton. So if you look at the steel chips we are getting around 1,274 metric ton. Aluminium we are getting around 73 metric ton, and the titanium which is much less in our system. So how we can collect it and how we can use it, that is the process. Here you can see we can have a production of this material, and then we collect them into here I can show you the graphical representation of the plan of present research work. The magnetic separation of the SGC from byproduct of slitting of mild steel was carried out. Subsequently, SGC particles were baked at 200 degrees Celsius for 4 hours to evaporate any residual of the coolant or unburnt volatile material. And afterward, the SGCs was compacted in a stainless steel die and then sintered at very high temperature in argon environment. The densities, micro hardness, and dielectric constant of these materials we are studying. So basic aim is that we have collected these kind of chips as well as the particles, and then we processed them, and then we study them by compression, sintering, and then we study their mechanical properties, structural properties, and the electrical properties of these materials. If you look at the morphology of these particles, they are having a very spherical morphology. And if you look at their phases, the structural phases which they are having, they have a iron oxide in a megamite and magnetite form, and alpha Fe also in the form of the X-ray diffraction. Studies show that. Then we can see their surface morphology, and when we sintered them, and after sintering, we can find their morphology of these particles, which has a iron oxide particles. There are some pores, then mild steel chips are present into that after a sintering of these materials. So to obtain defect-free component towards the powder, and is very important parameter of their processing through powder metallurgy. And what we did, hence the same has been evaluated for pre-processed via standard method, found to be suitable as shown in a table. The apparent density we have measured, then tap density we have measured, then we have found the Hausner ratio and Kerr's index and angle of repose of these waste particle itself. So if you look at the standard data and considering these parameters like Hausner ratio, if the order of 1 to 1.11, and Kerr index should be less than 10, then this material is excellent for the powder metallurgy point of view. And if it is reduced, Hasner ratio is increased and Kerr index is also increased, and then there is a good and a fair. And in our case, in this kind of waste material, we have a Hasner ratio is around 1.26 to 1.34, and Kerr index is 21 to 25. And this is, we can say, it has a passable material to process. So very free flowing. And in our case, these are the cohesive type of material we have got. And if you look at their density of the MMC and the strength corresponding to that. So if you look at the density, it is a mild steel density is 7.78, and this MMC density is 5.12. And if you compare with the micro hardness, it is almost 3 times higher than the from the mild steel. And their yield strength is also, you can say, 3 times than the yield strength of the mild steel. And the specific micro hardness is also enhanced in a greater way. And the specific yield strength is also almost, you can say, 4 times than the mild steel. So then finally, these materials we found, and they have, we believe that they have a core shell type of structure, which we already studied. And if you have a core shell type of this kind of a material, and they will show a dielectric properties. If one can look at these data, we measured the dielectric constant as a function of a frequency. It is having a very nice dispersion relation, and at around 1 kilohertz, their dielectric constant is around 1600 or so, which is a very large dielectric constant. And if one can look at the dielectric losses, these materials are having a very less dielectric losses in the range of 0.2, 0.3, like that. And at high frequency, the dielectric losses are very low. And from there, we can also calculate the imaginary part of the dielectric constant in a system, because it is a dielectric properties are the complex property when you have as a frequency dependent, and they have a real part, which is the chi prime, and another is the loss part is the chi double prime, and the ratio of these will lead to the tan delta of these material. So when the loss is less and the dielectric constant is high, we can say that these material can be used for various kind of application, like a transformer and another kind of application where the high dielectric materials or high storage energy capacitors can be made out of these material. Now, how we can explain such kind of high dielectric behavior of that? This is inherent in their production itself. When I can talk about their production, it means when these grinding or machining processes occurring and these particles are flying and they are at very high temperature. And at high temperature, when they are exposed to the environment and their surface will get oxidized and the inner part should remain as a metallic. So one can say the core is a metallic and the outer part is oxide, because the time of flight while exposing at a high temperature is very short. In that sense, it is not a fully oxidized, but it can have a core shell type of behavior, which we have shown through this TM picture. So now when you have this kind of a system, you have a oxide, which is a dielectric, and you have a metal, which has a resistive part. And if you look at these overall, the core shell structure of that, it will represent to the RC type of circuit, which can give rise to the high dielectric and high capacitive system. That's why I can say these material which we throw them as a waste material, if we can collect them in a proper fashion, we can use them from their mechanical property point of view. There's all the mechanical properties are enhanced than the mild steel. And from that, these materials are very useful from a mechanical point of view, as well as the new property which we have explored for these kind of waste material. These are very good for the electronic devices, where we need not have a material in a large quantity, but we should have a material in a small quantity to make the devices out of that, where the electronic devices where we need a high electric material can be utilized. So we finally model this system. And in conclusion, the successful fabrication of the metal matrix composite through the powder metallurgy technique rendered this work as a unique. Further, the physiomechanical and electrical response of these SGS and MMC are enlisted. So SGS are lighter and harder than the parent material, that is the mild steel. MMC contains multi-phase material containing mild steel chips and iron oxide. The dielectric measurement suggests that the high value of dielectric constant found in the range 242 at 1 megahertz, 242.6 dielectric constant at a very high frequency. So high frequency devices, these material can be used, which has a large, whereas another kind of ferroelectric materials we are using, they are having a very strong dispersion, and their losses are also high. So can be the best candidate for the fabrication of nano hybrid material in a energy storage devices. That was the conclusion. Thanks for your kind attention. Any question, any doubt, we can discuss.
So thank you very much, Professor Ravi Kumar.
Yes.
I'll discuss if any question in question session, just followed by your.
Excuse me, because I have one meeting is going on. If regarding my presentation, any question, otherwise I have to leave, and I left the meeting and came here for giving this presentation.
Thank you, Professor Ravi Kumar. May I ask you one question, one query?
Yes.
Question, not question, it's a query. It's a wonderful work you have done. That milling, grinding, and turning, whatever waste materials are coming, and that you are making through a powder metallurgy process. You are making nanohydrate materials, and which can be utilized for the energy storage devices. That is what is clear to us. Can you please tell me what should be the waste material? Whether it is a 10% you can utilize, 90% you can utilize, or any other percent? Because
this depends. Basically, most of the time, wherever we are having these kind of machining work is going on, we are not properly collecting these kind of waste material. So my student and myself has designed a way how we can collect these kind of material. Because generally, if you visit to any workshop where these kind of work is going on, they they will spill out these kind of material. So here we have made a very nice arrangement, put a box around that with some magnet placed on the surface of the box. And we are collecting these material. As I told you, we may not collect that material in a large quantity, but whatever is required for the energy storage properties and some mechanical properties, we have a sufficient amount of material we are collecting from these our kind of applications in this material.
That is okay. That is okay. My question is, my query is, how much waste material can be utilized? Whether you can utilize 90% of that or 10% of that, whatever is required for dielectric materials is okay. That means we can make energy storage devices. But suppose I am producing 100 tons of materials. So out of 100 tons, your technology, how much it can utilize it? Whether 100 and 100, totally 100 tons can be utilized, or 90% of that can
it is not possible using 100% material, because as I have mentioned in this technique, in this slide, how we are processing our raw material.
Okay.
So I can say around 60 to 70% is the material is useful in this kind of a process.
Okay.
Because we have to wash it, we have to magnetically separate out, and then we have to sinter it and getting those kind of a final product.
Thank you.
So Professor Ravi Kumar.
Yes, sir.
I have say question as Dr. Bhoi sir said. Say similar situation is with us. In case we go larger scale, utilize your say mechanism. Say we have a say water separator, and then we collect it into a magnetic box so that
yes,
can be separated out, and then subject it to drying and sintering operation. So we can make pellets on larger scale, I think.
Yeah, why not? That work which we have mentioned here, these all are on the pellets. And you can see the SEM, this is on a pellet SEM, this is on a powder SEM.
Yeah.
So we make a pellet, and then we can measure the electric properties, because the electric property on a powder, it's not possible. So mechanical properties are also not possible without pellet. So we sinter the pellet as here at 1150 degrees Celsius in organ environment, because further oxidation we don't want. As I told you, the formation of core shell itself is a very tricky, it's a instantaneous process.
Yeah.
If I will anneal this into the oxygen environment or ambient environment, and that slow heating and slow cooling will oxidize my whole material. So my purpose is lost to get the core shell structure of my material.
Sir, can we take help of NIT Hamirpur in getting some sample pellets made at your place?
Why not? Why not? My student is also working in our workshop, because he was a workshop scientific officer who took his PhD work with me. He's a permanent employee. And whenever you contact us, we can produce the sample for you, as well as we can, if you have your sample, we can process them also.
No, we are basically charging this after drying and dewatering and drying. We are charging into AOD furnace.
Okay.
So we are charging along with the grinder, say whether it's a silica grinding wheel or alumina grinding wheel. So all that sludge is also going along with that, and we are wasting energy on that, because the chips are hardly grinding chips are hardly 10%. Our material on centerless grinders is around 8 to 10% of the diameter of the bar.
Okay. So, yeah, you are right. The process I have mentioned here, all these processes. Yes.
So that way, around 2,000 ton of material, we are producing something like 500 to 600 tons of this dust.
Yes, yes.
That
So
is
that is the what, because we have a thought about this. Earlier, my work is on a fly coal ash, and they are composite with the iron.
Yeah.
And we showed that how we can reduce the density, as well as we can use the waste material like coal fly ash, and that project even worldwide people are appreciating our work. And now we thought that how these kind of waste can be managed. So that is the laboratory level we have initiated this process. And if you have an industrial level, one can think of and one can sort out this problem. And very interesting material we are getting out of that.
Yes, yes, yes. We are getting recovery even today.
Yes.
Getting recovery, but at a special cost. That is why it made me interested to be in touch with you and get some solutions.
May I know your good name?
I am Dr. Shivraj Singh Kasana, sir.
Shivraj Singh.
Yeah.
Because I'm not seeing the screen while talking to you.
So thank you very much, sir. Thank you very much.
Okay, thank you. Because my colleagues are waiting for me in the meeting, so I have to quit that. So see you. Thanks, Nas.
Thank you.
Thank you, sir. You can close your share screen, sir. You can close the share screen, please.
Stop sharing. Yes.
Yeah, thank you. Thank you, sir.
Okay, sir. Okay.
So
anytime you wish, we can, my phone number, you can write down. It is a 98.
Yes. I'll be in touch with you, sir. Don't worry.
Professor
your details.
Professor Ravi Kumar, I am Dr. Bhoi, the Chief Scientist of IMMT Bhubaneswar. I am also, my team is also working on the waste to wealth materials. And we are working with all the minerals like, different chromite overburdens and all these mining wastes and all. There we are making different alloys and all. So my team, if it is necessary, will be in touch with you. And we'll.
Thank you very much. Basically, this is my side business. I am a condensed matter physicist working on a transparent conducting oxide materials and their devices. And this work is my side business. Just I thought now end of my career, I should devote something to the society.
Thank you.
Dr.
Oberoi.
Yes.
Sorry for interruption.
Yes.
I have also certain important meeting. May I leave this with your permission?
Yes, sir. Please continue, sir. Thank you for joining, sir.
Thank you. Thank you, Dr. Kasana also.
Yeah, Dr. Bhoi, thank you very much. And it proves the necessity of such webinars. And basic purpose of the seminar gets solved in case you have such an interaction on the forum.
Thank you, sir. Thank you very much.
Sharing your time, sir.
Thank
you very much.
Dr. Kasana, there are certain question answers.
The first question is for me. So, as far as I know about the failure of Columbia shuttle, the various kind of explanations have been given by NASA, and say the version they have given is that the Columbia has lived its age, and they did some cost cutting also at that time, and the failure actually happened because of falling of foam from near the fuel tank. It fall on certain area of the tiles, and it broken up on the glue which fixed the tiles, and 1 or 2 tiles gave way first, and then some 20-30 tiles got burnt, and which created the fire on the Columbia shuttle. While reaching back to the earth, they took it say for investigation. By that time, the Columbia shuttle reached for investigation. Some 2,000 tiles got damaged. So it is certainly basically because of material failure and some amount of workmanship into their say construction of the body of the Columbia shuttle, including say tiles, gluing, as well as the placing of the foam, because which got dismantled from somewhere and fall on the tiles. So which local damage it created, and which because of facing the very, very high speed of returning to earth, created fire. So that is what is the say answer from my side, so Rajshri Sarkar. So in case you have any doubt, you can read it through. The NASA report has been there. You can read through the NASA report. Okay.
Yeah.
Then there is a question from no, it's regarding the voice. So how can we identify the types of plastic deformation in metals under electron microscope? It's simple. I think Dr. Raj Bahadur will be the best to answer this.
I think, sir, the question itself is not clear. Means how we can. He want to know about the process. You want to know the mechanism, or what you want to know actually. Basically, there's no.
He want to know basically what it indicate in case there is some plastic deformation. Basically, indicating the density of dislocation.
Dislocation density, you can say.
Boundaries. So he can do it by putting the EBSD detector, or maybe even secondary electron detector will also show some traces of stresses and all. This is what I feel. But in case you have any expert opinion about that, you can please give.
Yep. You can see this microstructure, the deformed microstructure and deformed microstructure you will identify easily. And obviously, after a severe plastic deformation, the grain will be refined, and then the below 1 micron. So you can identify in that way.
Okay. What happened? What happened?
So do we have any other questions, sir? Or we can go ahead?
Any other question? There is no question, I think.
There is one question. Couldn't we just use natural materials like wood, clay, and straw instead of completely relying on using metals on everything and recycle it back? Basically, they want to just ask that whether why should we recycle metal and use metal more rather than using wood, clay, or straw? But that's a prerogative of the design and requirement. I think we cannot challenge that. That is my view. Any expert view on that?
Yeah, definitely, sir. We cannot use means you cannot replace the metal with these things. Huh? You cannot replace the clay and all. So the metal and alloys have distinct properties. So you cannot replace totally. Partially, you can replace sometimes, but.
There is any more question?
I don't think there are any more questions, so I think we can go to the next. Take up the video permission. Can I take up the vote of thanks and for the webinar?
Yeah, I think we should.
Because we already we have reached our time, so I'll deliver the vote of thanks. Very good afternoon, everyone. Respected President, Engineer Chinmay Debnath ji, who couldn't make it because of paucity of time and he was busy, his busy schedule. Chairman, Metallurgical and Materials Engineering Division Board, Dr. Bhagyadhar Bhoi, Chairman, IEI Faridabad Local Censure, Engineer Kuldeep Raj Gupta ji, our distinguished speakers, my fellow FLCC committee members, and all the audience present. On behalf of the Institution of Engineers India Faridabad Local Center, I take this opportunity to propose vote of thanks to those who have directly and indirectly contributed to this webinar on advanced materials, synthesis, characterizations, and application in metallurgical and material engineering division. I would like to express my sincere gratitude to Mr. Debasis, Mr. Sudeep Chakravarti and their team for their unflinching support. My sincere thanks to all the valued speakers, Dr. Raj Bahadur Singh, Dr. Hitesh Kumar ji, and Dr. Ravi Kumar, for making excellent presentations and making this webinar interesting and meaningful. I'd like to add one more point. The purpose of these webinars is interaction of industry and academia. And we just saw that our speakers from academia had a wonderful association regarding industry and solving industry problems. And that's the prime objective of these webinars conducted by Institute of Engineers India. I extend a really hearty vote of thanks to our President, Chinmay Devnathji, Chairman MMDB, Dr. Bhagyadhar Bhoi, who spared time from their busiest schedule to grace the occasion. We are really delighted with your knowledge and presence. My special thanks to our event moderator, our own Dr. Shivraj Singh Kasana ji, who is a valued Faridabad Local Center Committee member, for the unflinching support and making this event a resounding success. Last but not the least, I thank all our II members who have joined in and all the participants.
टच में रहना और बताते रहना. After
blessed
some
with their
यहाँ पे
presence
आने के बाद
and who
कोई
took
problem
valuable
वगैरह
time
की let
from
me know
their
मैं
busy
करते ही
schedules.
रहूँगा कोई.
Your presence and participation make this event up to the mark.
नहीं वैसे अगर later
These
on भी
warm words and kind message, we move to the end of today's webinar. Thank you very much for attending the webinar. And I now request our chairman, sir, to give us permission to close the webinar. Thank you, sir. Thank you. So we'll take leave. Thank you. It was a wonderful interaction. Thank you very much for joining us.
Thank you, sir. Thank you, sir. Thank all of you.
Thank you very much.
Please close the webinar, sir. Thank you.
Thank you, sir. Thank you all.
Thank you very much.